I
think we can start. So, hello and welcome everybody to the world premiere of this talk. Because no editions before that existed, this will definitely be the worst and the best and the first. Hopefully not the last, but we'll see.
Should I?
Yeah, about us. How do we know each other? It's a long story, but the details are not that important. Let's start with Jarek.
Okay, so I'm Jarek, I live here in Krakow, and I work in Neo4j as what I do? I destroy production professionally. So if you need somebody to destroy your production systems, just call me. I do it like with ease within 50 minutes. And I work in the benchmarking team as a team lead, trying to break the database for the last 7 years. And yeah, you may know me complaining about JVM people and architects. Yeah, we're going to have this dance, yeah?
My name is Andrzej. I go by Axe because apart from Polish people, nobody can spell and say Andrzej properly. I work at a startup which is called DataLinks, which is trying to bring context into AI. It is not a database. We might end up using Neo4j for one of the things that we do. So this is not a database. He's doing a database. I've been coding. I've been running this. You've seen me doing the opening. I also am involved in GeeCON and some other icons. And today we're going to talk to you about log-free. Why log-free? What is log-free? Yeah, why?
Does anyone know what is log-free?
Yeah, I hear some voices. I don't see any faces because the lights are blinding and they are not approaching, so it's not a train.
So they don't know, so we can make up things like lie. You know, because actually the last commit to this presentation was 20 minutes ago, so I would say low expectations. So what is log-free, Andrzej?
Well, it's easy. If you want your software to go fast, you take out all of the logging code, and then you get log-free. Is that what you're asking?
The log4j free.
Yeah, log4j free and everything.
So yeah, this presentation is about log4j free code.
No, this is a talk about how to make your software a bit more towards sanity. I will not say guarantee sanity, because if you've heard Ryan's presentation, the way to get that is use 0 or 1 thread, no more. But how to think about your software, how to model the changes and what are the building blocks so that you can get some nice benefits, like easy to think about things, and maybe sometimes performance. And when I say performance, that's obvious, but when I mean consistency and all of that, it boils down to progress guarantees. So what can we say? When can we say that a change has happened? It has been applied to a state of a system, and so on and so on.
So what are progress guarantees? And this is like the last important slide in this presentation. So if you have a concurrent structure and concurrent algorithm, what you want to make sure is that at some point of time, they will finish their job. And it's not that easy. It's simpler with single thread. In concurrent programming, you have this concept of progress guarantees. So how we make sure that with concurrent program, logs and mutexes and all these barriers and lovely stuff.
Synchronized.
This is our favorite topic. We can do synchronize for hours. Bashing, of course. So what are the levels of the progress you can guarantee with your concurrent algorithms?
So there is a couple. The couple is there is a couple of categories, or there is an increasing joy, there is increasing happiness and greatness level. The first one is obstruction-free. Nothing will get obstructed. It's the weakest. It means a thread executing in isolation. So, for example, on a single core, single-threaded system, it will make progress, whatever that means. And there will be no deadlocks, and everything will be good. As you can see, this is quite basic, but this is the basic building block. Then you can take it up a notch. You can get log-free. Log-free means there will be system-wide progress. So system as a whole will make some progress. Overall progress will happen. Individual threads can starve, which means the system as a whole moves forward. Somebody might be a bit unlucky. Somebody might have to retry a year, an exam. I don't know what. Depends on the context. And then there is another level called wait-free, which is the strongest, which means every single thread, or every one of many threads will complete their operations in a finite number of steps. Finite does not mean small. Finite means not infinite for this context, which means they will eventually finish, and that's a guarantee. So today we're going to talk about log-free, and as you can see, which is important, log-free does not mean without logs. We'll talk about it more, but I wanted to already highlight that because that's...
You know, as always in computer science, the problem is naming. And the naming log-free creates a lot of mess in our brains because we say, oh, okay, this is no locking, which isn't true.
We'll get there.
Yeah.
And of course, dry jokes.
Yeah. It's all about freedom of choice. What log-free means, I think this is like a really good entry-level blog post on log-free programming. The examples are in C++, but you know we have ChatGPT, it can translate it to Java, so we are fine. But I really like this sentence, that in log-free programming is not about not using logs, it's mostly that the system as a whole will not lock up. So you will not have a situation that all of the threads you have are not doing job. So what I like to think in log-free programming is at least one thread is doing something, yeah? Something meaningful. The rest of the threads can do something useless. You will see it later. But in log-free programming, at least one thread is doing something meaningful. Oh, not this slide, sorry. So what is the heart of log-free programming?
Read a value, change it, write it, so publish the change, and then hope everything is good.
Can you have a small quiz?
Say again?
Can you have a small quiz?
Of course.
Okay. This is all random. You know, we improvise.
But you have Slido. You can ask us questions, and you can ask questions, and they can answer in Slido.
There is no prize for the right answer, but is it thread safe? Nope. It depends. It depends on the architecture. I didn't know you were here. So it depends. Okay, but let's assume we are on Intel, or it's worse, we are on ARM. And we make it volatile in Java. Is it still safe? No. Okay, so we are at the right conference. Why? Because if you think about it, in your head, it's single instruction. The truth is, for CPU, it's at least 3 instructions.
But how? Something. This is for characters. This should be simple.
It has to be log-free because it's in one line, yeah? So I'm thread safe. Because you need to read things, and then the other threads can come in and also read it. You need to increment the thing, and then you need to write it down. And in all between these two operations, something can happen, yeah? The other thread can come in and modify the value.
Or we can both read the same value. I will try to increment it. You will try to increment it. I will write mine. You will write yours. If we started at the same point, we'll get to the same result. But if we didn't...
I like this idea for my bank account, you know.
Yep.
So how you achieve this safety, the thread safety of this operation using the atomic operations?
I assume you all know Java util concurrent and the atomics in there, so you're familiar with atomic long, atomic double, wink, wink. I had to. And other things like atomic reference.
Who recently imported Java util concurrent package?
I see hands in the audience. Awesome.
Last time I asked this question in some city in center of Poland. Sorry, no personal.
So how does it work? How does atomic work? Why is it so magic?
So atomic operations are basically operations on a single memory location. There were some attempts in the past, like in Motorola CPUs, to do it on 2 locations. But who remembers Motorola CPUs? But basically, you have an operation on a single memory location. And this looks like a transactional kind of operation because you get all or nothing. So when you modify, do read, modify, and write, your program, your code sees this as a single operation. So there is no way you will see stale values in between because it's single operation on the smallest possible level. And I read this comment on Stack Overflow. I think next year we'll say bye-bye to Stack Overflow. Have you seen the numbers? Yeah, all the humanity knowledge is going.
All hail our AI overlords.
Yeah. So this comment was that atomics are the smallest possible log on the hardware level. I like this comment, but actually atomics are logs. Down at the bottom, there are logs. but on the smallest possible level. How it happens at the CPU level?
Well, CPUs interact with memory using something called cache lines, and that means that an atomic is effectively going to be transferred into a cache lock. We are not going to get into messy and the details and having multiple CPUs because that would take many hours for us to prepare and then many hours for us to present it. But you can think of that as a hardware level lock at a cache.
So basically,
level.
whenever you do atomic operation, for example, on Intel, you have this lock prefix, special prefix on the assembly level. It goes to the bus you have between CPU, between cores. So imagine that actually your multi-core system are distributed systems. And inside every CPU, there is Kafka-like thing. You can think about it. But CPUs publish some messages to this bus, and they respond to messages, and this is like small distributed system in a nutshell. So basically what happens is the CPU that does the atomic operations sends the message, hey, I need this value, and it's mine, only mine. The others can respond, oh, sorry, because we already own this value, but when there is no other processor owning this value, it becomes exclusive. The cache line goes into something called exclusive mode in messy protocol, and then nobody else can modify. Everybody needs to wait. Yeah, so it's small distributed systems.
There is a lot of fun there,
Yeah.
but...
So what kind of atomic operations you have?
Well, you can say more, but at the basic level, there are three usual atomic basic building blocks. The one is exchange, which means you have a value, you want to exchange it for another value, and you do it atomically, which means what it means, but you exchange one for the other and not for something else, which means if you wanted to exchange it and somebody changed it in between, it's going to fail.
So basically, you want to write new value, but you want to get the old value.
I pretend I know the old value, and if that old value matches, then I get my exchange.
Yeah, and this is one of the atomic.
Another one is exchange and add. So I want to increment something, add a value somewhere. We add things in computers quite a lot, and exchange it. And another one is compare and swap. So I think I actually described that at the beginning. Sorry.
Yeah.
So CAS, sometimes it's referred to because who can be asked to write the same words over and over. But compare and swap is what we do a lot because it's useful, because we only exchange if our expectations matches, which means the preconditions, if I want to use a fancy word, match.
So basically, in compare and swap, you only change the value if your old value matches with the current. Okay?
The code, I think, explains it reasonably well.
Yeah, it's reasonable.
Good. Let's have a look at how it's implemented. So this is Java. As you can see, it's Java because you can see the amount of C++ and actual assembly. But this is how, under the hood, the JVM does this. What you can see here is it does some asserts. And I think we missed to mention the file. This is a file specific to a specific CPU.
This is Linux x86.
Yes. So another CPU or another flavors will get different files so that the assembly matches. ASM, volatile, fun.
So what actually Java does, depending on your platform, it will use specific intrinsic and will say, like the operation compare and swap, the method call in Java will be changed in JVM on the Intel CPU into the single compare exchange, and you see the lock prefix here. So we require locking the bus, the cache line, when we do compare exchange, and this will be your method call. And depending on the platform, you will have different instructions. Yeah. Why we are talking about it?
Well,
except this is C++
and assembly.
And assembly code.
And you're here on a Friday after lunch, so being relaxed, and we throw such bad things at you. It's because you can get those big numbers. What was the benchmark?
The benchmark was really simple. So I was incrementing an integer using multiple threads. And I used different ways to make sure this is thread safe. So I use atomic integer. I didn't use any synchronization at all, so this is like my baseline. I'm not doing any synchronization. The results at the end will be wrong, but at least they will be fast. All fast software is, in most cases, wrong, but it's fast.
But also, if you do benchmarks, do it in a Sentinel, because then all of the results are really big.
Yeah. And then I protect my integer with read-write log, run read-write log, and yeah, I do our favorite synchronized. And this was done on 4 threads reading the value of integer and 4 threads trying to increment the value of integer on this pretty old AMD Ryzen 7. So this is this laptop. As you can see, the atomic is much, much faster. This is operations per second, so we have throughput. Higher is better. So atomic is even faster compared to not synchronized case, so the plain access.
That's curious.
That's curious, but it's another discussion about the cache hierarchies. So these are numbers, but I believe in pictures. So this is the difference between synchronizing access to this integer using atomics. This is like skyscraper, and this is typical Krakow building. It's rather small. We don't have a lot of skyscrapers.
Hey, but you can say that atomic is 5 meters fast.
Yeah.
Or
It's
maybe.
really fast compared even to read-write log and synchronization. So mostly when we are talking about the log-free programming, we are talking about it in the context of speed and latency.
And you know about CAS, you know concurrent swap.
Warning, this presentation contains code.
Yeah, sorry. But people are asleep. It's after lunch. And I have coffee. How to do log-free, or what will it boil down to us? And there will be some amount of changes that are done, code that does the work. And we will be using queues for examples because they are simple and they are typically used for examples.
This is stack implementation. Surprised I did it 5 minutes ago.
I am not surprised at all. What you can see here is there is a node, self-explanatory. There is something called atomic reference of a node. That's an atomic pointer, but we don't say pointers on the Java side of the world. And then there is a method called push. Comments are self-explanatory, so you can read what they do.
OK. So we are trying to push something on the top of the stack, and we want to do it in a log-free manner, so we don't use logs and synchronize. What happens is, at the beginning, we create our new node with our new value. We want to push at the top of the stack, and then what we say, we read the current head, so the top of our stack. Then we try to link the new node with the old one. So this is the moment when we say, OK, let's connect the new node with the old one. That's how we create the stack. And then what we want to do is compare and swap. So this is this like line we are interested, because what this does is we only install new head if the old head didn't change. OK? Are you with me? That's like Friday code.
Oh, I will be the stupid person in the room. I will be the most stupid person in the room. Why that? Why not just replace it?
Because this is the comment. In the meantime, the other thread or other threads come in here, and they can get more CPU time. They can be more lucky. Maybe they have higher priority, or the CPU likes them more for some reason. And they will change the reference to the head. So then you will have an old head. So it means you will install the new node somewhere in between, not on the top of the stack, but somewhere. Or even you can lose the reference.
That would be sad.
That would be sad, because you will get the inconsistent structure. So what we have is say, OK, if the old head didn't change, OK, so this is our atomic. This is the old value. If it didn't change, everything is fine. We are done. If something changed in between, some threads came in and changed the value of the head, we retry. So we fetch again the current state. We say, OK, what's the current state of the head? And we try to do, again, linking. And we try.
So in the case of a single thread, this will work without any problems. In case of many, one of them is going to win somehow. The other one will have to retry. So if you remember the guarantees, some threads in the system are guaranteed to make progress. the threads that win, they install their new element, and the ones that have to retry, well, they didn't win this time, maybe next time.
Yeah. So maybe something complex right now, a little more complex example.
And a bit older than 20 minutes.
And and bit older than this one. So because queues are everywhere, and after 30 years in IT, I think the queue is the most important data structure in the history of this business.
Well, I live in the UK. Queues are extremely important.
Queues are part of it. And I'm from Poland, and I'm old to remember the queues, in shops. So we are going to talk about log-free implementation of a queue following the Michael Scott algorithm, and we'll try to see something more fancy. Yeah.
So what are we going to do? We want to have a queue, and we want to put data onto the queue. Easy. There is a fancy diagram. So the initial state looks like that. There is a head. There is a dummy node. The dummy node serves a purpose as a dummy node that needs to be there. Then there are two nodes already, and then we have a tail pointer.
So this is our end of the queue. Yeah.
So that if you want to read it, well, you can, and that's where we start. We want to add yet another, so there will be node number 3.
Okay.
What's happened? So we make the new node.
And nothing changes yet.
New node doesn't know where to point. Nobody points to the new node. You've just said new node, like in Java with new and so on. Or maybe you use the factory method, something. And then what do we have here? We want to link it. So we have two things to do. We have to make the last node of the existing data set point at the thing that we just created. And we need to make tail point at that newly created thing.
So we have two operations, yeah?
Yeah, and because we don't have the multi-atomic operations as a thing, we have to do it in two separate operations in a way that somehow maintains sanity. The first step that you do in this implementation is you cas install the new node. So the node 2 will point at our newly created thing. And then somebody could say, hey, but the tail is pointing at the old data. And you would be right. What happens then?
So the problem is that the oldest node now has a link to the new node, but tail still doesn't know what is the new node. Yeah? We just replace the pointer from the next field in the node to point to the new node, but tail doesn't know. So if somebody comes here at this moment in time, the other thread, he will probably, if something goes wrong,
or she,
whoever, some random AI agent, will come here and will get the old one, but we just inserted the new one.
That can be something that you can accept. It might be inconsistent and you're okay with that. Usually you expect computers to be a bit more consistent, so we have to do something.
So there is another cas operation that will happen that will say, okay, now my tail is this node. Okay, so we need to relink. We need to remove this reference, this link, and replace it with the new link.
So we do it, and we're happy.
So sometimes there can be a situation when the new node is the oldest node is already explaining code with hands. The oldest node is already pointing to the newest one.
We've added the new node. The tail is still pointing at the...
Yeah.
Is this inconsistent state? Can there be a way to detect it? Can we do something about it?
We can. Code.
Of course.
So at the code level, I need to wear glasses. That's disgusting. Oh, now better. Now everything is beautiful.
In the meantime, there was a question, are there any gotchas for log-free with native Graal VM? I have no idea.
I haven't heard about one. Yeah, it shouldn't be, because the Graal VM will use the SDK, JDK code, and JDK code has intrinsics generated from assembly, so I wouldn't expect any problems unless they screw up something, but I don't expect it.
And log-free paradigm does not guarantee fairness in accessing resources. Yes, we didn't use the word fairness because...
It doesn't.
It doesn't. If you care about it, it's a separate discussion, which we will not include, I think, in this talk.
So let's go to our offer method, and then this is what we have on diagrams. what we do in the first step, we take the tail, and also we take the node that points to the tail. So we have the tail, and we have the latest entry in our queue. And this is interesting. We check first if there is a situation that other thread created new node, but we are running in the middle, and the new node is not yet connected to the tail. Okay? So we try to fix this situation first. It's like helping your neighbors. I know we are in Poland. It doesn't happen often. But I'm from Poland, so I can say this. So it's like helping the other thread, saying, OK, you created a new node. You cast the new node to the old node, but you still didn't cast the tail to the new node. So I will help you. And once I help you, I will exit and will try again, get the current value of tail and current value of the latest node, and then compare and swap and replace and connect the nodes, and then connect your node to the tail.
And you can see that happens in a while true loop, so which means
we keep trying.
We will keep trying.
It's like competing with your busy worker.
In an optimistic case, it works. In a pessimistic case,
in optimistic case, it will take one iteration of a while loop. In pessimistic, it will take ages if you have a lot of threads competing.
In a really pessimistic case, an asteroid will hit this planet and so on.
Okay.
So, have you noticed the pattern? Most likely, because we hope that it was big enough. You try, you read some data, you make your changes, and then you try to publish them, and you only publish them if the state of the world that you did the changes upon matches what is the state of the world. Anybody here uses Git? You're familiar with it.
So it's your everyday. So Git is log-free. I see some old people here. Do you know things like source safe?
CVS, not the pharmacy.
CVS didn't have this problem, but there was this version control system when you were pushing changes, it was locking the files, so nobody could pull and push. And imagine I was in a project when guy checked out the repository and went for vacation, leaving the lock on the whole. How it's called? Not source safe.
ClearCase.
ClearCase. Yeah, ClearCase had this thing. Yeah.
Yeah, we both worked in the same company that happened to expose us to ClearCase, and it was pure joy.
So working with log-free code is like working with Git. You pull your changes, you pull your current state, do the work, and try to commit. When somebody committed in the meantime, you need to rebase it. So basically, if we try to go back, oh, this is my fancy slides with me dancing. You see, this is a good example. We pull the current state, and we say, OK, what's the value of the tail, and what's the value of the node? We do our changes, and at the end, we try to apply the change. And if it fails, we go back and we try again, reading the value, because if it fails, it means somebody probably changed the values in the meantime, some other thread.
We talked about that.
Yeah. How do you prove that it works?
Excellent question. So
I asked Andrzej to dance, to do this move.
I respect you and I will not dance. That's why. There is a tool in the JDK called JC Stress. And JC Stress is only 10 years old. And they mentioned this funny line. Java concurrency stress is an experimental harness, underline is ours, and a suite of tests to aid the research and correctness of concurrency support in the JVM class libraries, blah, 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 blah. The trick is, this is how you test whether your algorithm is not wrong, but what you get is a guarantee that it didn't crash. It doesn't mean that it's correct.
Yeah. And there's one thing I like about JC Stress, because it tests your understanding of concurrent systems, because sometimes it can say, OK, you got it wrong. So how you can prove that this code is thread safe using JC Stress? So basically, JC Stress has this concept of actors and arbiters. And how it works, you write small, tiny methods that do something. And JC stress invokes these methods from separate threads millions, hundreds of times, and it tries to break your system. It's really interesting. That's it's called test stress, because it's basically running in a loop from multiple threads. Every actor will get its own thread. And what happens, I know it looks weird, but basically what you expect in this case is either both consuming actors will return null because the actors will be invoked before you do the offer. Yeah. Either one of the actors will get something, yeah, so it will not return not null. The wrong case is if both actors return the same value. Yeah? You don't expect from the queue to return the same thing twice.
I put one chicken in the fridge. If 2 chickens can be extracted out of it, there is magic in the world.
Yeah. So basically, if you run these examples, we can share the GitHub later with these examples, I think, so you can run it on your computers. Basically, this implementation works and it returns only one value for one thread. We need to check one more thing with JC stress. This one more thing is that happens before relationship. So we need to guarantee that if we call offer before poll, we get the value. So this is the happens before relation from the memory model. Because this example, the previous one, it just proves that we won't see the same value twice. And then we need to prove that when we call offer before other threads, we will see the value.
So when we try to
how
publish,
we do it? We use arbiter.
Yeah.
So this is the thread, but it's like once it calls all the threads doing this job, this will be done. Calling arbiter, you make sure that this is invoked after all actors do their job. So what we expect, the current output is, this will return not null, and this will return null. So this is how we prove the happens before with JC stress.
Yeah. Concurrency is great. There are jokes about adding concurrency to an existing problems and then getting much more fun out of it. If log-free is so great, why isn't it?
So popular.
Yeah, there are many problems that you can get into with log-free or anything concurrency. One of them is called ABA or ABBA without the B, whichever pronunciation you prefer. The ABA is...
Now you see me, now you don't.
Somebody tries to do something, they do the change, then something else happens, they make the state A again, and to the outside world, it might be impossible to tell whether there was a state change at all, because it's all A after.
I think it works better if you explain something using money, because this is what people can refer to. So imagine you have bank account, and your bank account is atomic integer because you don't have enough money to have atomic long. So you have atomic integer as your bank account.
At least not atomic double.
Atomic double. So what happens is one thread takes 100 euro from this account. But in the meantime, the other thread takes also 100, but also puts 100 into this account. And then the other one wakes up and says, oh, it's still the same value. You know, you do the cast, the value didn't change. I can change the value because everything is fine. So this is called the ABA problem, because you see A, and then you see BA, and at the end, the other thread thinks, oh, that's cool. Nothing has changed. So what can happen is, if you, like in this example with the queue, it can happen that something will take something from the queue, and in the meantime, it will remove it from the queue, and the other thread will not see the situation and will not put the value on the queue, yeah? Because the reference changed in the meantime. So it will make your system inconsistent.
Now, the tricky bit is it really a problem? It depends. And sadly, this depends on what you need out of a system. For some people, knowing that the value is A or 100, and that it's not something else, is enough. Sometimes you actually care that there was an intermediate operation.
Yeah.
Depends on your use case. How do you do a workaround around it?
So there are a couple of possible ways of doing it. One is when you have your references, keep the version. So whenever you change, you increment the version. So when you do cast, you not only check if the node didn't change, but also you check if the value of the stamp or some kind of mark didn't change. Okay, so you do the versioning, and then even if it's the same value, but the version is different, then the cast fails. The other thing is you put intermediate nodes. So when you have linked list, you have values, you have nodes in between other nodes which don't have values but are used as a reference point. So the intermediate nodes doesn't change and they don't keep value.
And
so you're free to cast on them.
Another one very nice way, or nice in some specific context, is immutability. You have an object graph, you create a new mutation to the object graph, you publish the new object graph, and everybody's happy, maybe except the GC. But hey, at least it will be correct because nobody can change it in between.
So you don't update the references, you create new references every time.
And then there is deferred reclamation, but we're in the Java world because we have GC, we will not talk about it too much.
Yeah, this problem is solved by GC, so that's why log3 is a little bit easier in managed environments.
Some examples?
Example, how to solve it. So there's this thing called log3 linked list. I love the title of this white paper. It's pragmatic implementation of non-blocking list. This is not pragmatic at all. Nobody ever saw Harry's linked list. Or maybe I'm just weird. Yeah. This is a stupid idea, really, because it's linked list and it's log-free. But we are bringing this example because it's a really nice way of showing the ABA problem. So how we solve it?
Before
in Java,
we
have this.
We have this magic class,
Yeah.
and you mentioned tagging. You mentioned storing versions. This is using exactly that. There is a method called concurrent set in this class that uses the expected and the new, but it also has expected mark and the new mark, which means not only on the values but also on the mark, which means two things happen at the same time. And if the mark matches and the expected reference matches, you're good. If the expected reference matches but the mark doesn't, that means you're probably ABA.
Let's see how it's used in the Harry's linked list implementation. So if we do it in Java, I think somewhere in this white paper there's a claim that it is impossible to implement in C++. So we have our markable reference when we store the value and this flag, true or false. And then what we have is, like, this is the core of this linked list implementation. This is the method to find the element you want to replace in the list. So you have some key in this list and you want to find the value. So what you do is we have double while loops. So we take the current state and we start to traverse this list from the beginning, from the head, as long as we don't see our value, okay? So we compare, and we are trying to find the value that we are looking for. So this is the end, yeah? This is the happy path. But something can happen in between. You will delete. So you traverse your list, and in the meantime, you delete. So how to make sure that you don't return the deleted thing in the middle, yeah? So this is a good example when we say, OK, we only traverse if the mark is false. Okay? So if the value of the mark is false, we are OK to go to the next node in the linked list. If the value is true, then it says it was deleted, and I will reclaim it. Okay? So maybe I will show the delete method. It will explain a little bit.
I tried scrolling on your computer, but I can't, so.
Yeah. So basically, the delete method uses the find method, finds the node it wants to delete, and marks it as true. So it doesn't delete the node. It just disconnects it from the next. So we set the reference to null. But we also say, hey, this is deleted. So the other thread that is doing the find will say, OK, I cannot return this one because it was marked true. Crazy.
Happy day.
Okay, so you do the lazy kind of deletion. You just mark something as deleted, and the other threads help you if they traverse the list. And as you can see, we have even double while loops. Sometimes it's called double cas. It's not implemented at the hardware level, except the Motorola CPU, because it's the atomic operations on two memory addresses, which probably will not be close together, so it's pretty hard. So what Java does, it takes your mark and your value and puts it in a nice box. So there is a kind of box with the value and the mark, and it tries to do the cas on this thing.
Did you just say allocate?
Allocate. Yeah, so imagine what happens. Every time you do this double concurrent swap, there is new object allocated. Whatever it's successful or not, it will allocate new object.
Which means if this is a very contented loop, and
what possibly could go wrong?
You execute it a lot, then you will see GC doing what it's great at, burning CPU cycles, heating up the oceans.
It's the Bitcoin generation heating up the oceans.
Yeah.
We are like 8 minutes to the end of the talk, and nobody mentioned Java memory model. This is like, in 80s, young kids were scared by black car in Poland, but the black car will come and kidnap your kid. That's in the 80s in Poland. Now we scared Java developers with memory model, trying to impress others, saying that this is so hard you won't understand it. So how is actually the behavior of atomic in a context of memory model?
Oh, it's very simple. Okay, I lied. The text definition is here. I'm not going to read all of that to you. Get is the same as reading a volatile. Set is the same as writing to a volatile. Concurrent set, and so on, have the memory effects of both reading and writing. And the lazy set and weak concurrent set, we will read for you. Leave that for you as an exercise to read at your own pace, because we will be running out of time otherwise. Also, weak and lazy are a bit more finicky. We will not be covering them today. So
next GeeCON.
Maybe next GeeCON. The question that everybody probably will be asking is, I come back to work maybe later today, because this is exciting, my eyes are burning, or maybe on Monday, and I am going to do something log-free. Should I? So is it always better? Should I do it at my job?
Somebody said no.
Somebody said no. I am going to 99% agree with you, because sometimes it depends. Sometimes you actually have to. When do you have to?
I think there are some problems we didn't talk about and try to sweep under the carpet. So this is log. So at the CPU level, these things don't scale. And it's even worse because we are getting more and more CPU cores. So more opportunities to call a log on the bus and on the cache lines. And our caches are getting bigger, and we are adding more layers of caching and more cores and inter-core communication buses, blah, blah, blah. So this is a really nice paper, worth reading, lots of examples and graphs. So these guys were... Charts. Oh, yeah, I cannot say graphs. I'm working. So they were evaluating different CPU architectures, different families of CPUs in a context of does atomic scale? And there are a couple of problems. One thing is something called wasted work.
So if you have two cores, you're trying to do the same on both. One of them wins. The other one wins differently. They get to redo the work. If you have a fancy Threadripper with, I think, 192 or 96, whichever is the actual number, of course, that they have now, one wins, the rest get to retry. If it feels a bit inefficient.
Yeah, so, the more cores you have, the more rework you will have, because the more threads will need to grab the memory, the latest memory state. It will cause contention and latency on accessing the memory. So funny things. That's
is-
the one problem.
There is a workaround. You can ask only one thread to do one specific kind of work and then pass on the work to another thread.
Are you
so
trying
that-
to convince me to code in Node.js or?
No.
No, okay, thank you. Another problem that they discovered during this paper is that on CPUs, using atomics disables the instruction level parallelism. So you cannot do many things at the same time and fully utilizing our CPUs. So it's even 30% compared to simple writes if you do atomic writes in the contented case. So you stop scaling CPUs, and especially this lovely feature, instruction level parallelism. Summary.
We already told you that. We already discussed it. We can jump through that slide. But it's really like working with Git. That's a good mental model if you need one. So, assuming it's Monday, I want to really use it. Should I write my own?
For fun, yes.
Uh,
Just to grab the understanding, but don't write production. Ready code. There are libraries, and somebody who spent more time in looking at the CPUs did already implementations of the lot of structures that are log-free.
They also did a lot of testing and bug fixing. And then you can come to the previous GeeCON, for example, talk to Nitsan, and then realize that he's actually the maintainer of JC tools.
JC tools. The other thing, even if it's fast for Nitsan, it doesn't mean it's fast in your case.
It's not a silver bullet. You should not always use log-free, but it's a tool that sometimes becomes extremely useful.
It's good to know.
It's good to know, and it's a fun thing to talk at a conference party. Some examples. I have to mention Agrona because we've had Dimitri here yesterday. I don't see him here, but I know in spirit he's still with us. There is obviously Disruptor because we have some LMAX people somewhere in the room. They might wave. You can ask them questions. Don't ask me questions about the Disruptor. They are the better souls. There is JC Tools, which I mentioned. You can probably find more.
Yeah,
and you
there
can
are
find
even
bits-
some log-free structures in JDK.
And if you grab the JDK source for log-free, you will find even more, especially on the CPP side. I know scary, but it's being used there.
But it's one important thing worth to mention. Read the Java docs, please. I know reading is like hard because it's like more than a headline. It's like
But you can ask ChatGPT to summarize it for you.
Yeah, summarize in Java doc as a service. My new startup. So read the Java docs because even in concurrent hash map, I think it's concurrent hash map, there is like slight, small notice saying it's log-free, but not in all cases. Because sometimes they need to fall back and use log and synchronize. So it's never like 100% log-free. Sometimes you need to just say, okay, I try a couple of times. And this is quite popular even in synchronized implementation in JVM. They try to CAS for a couple of times, and after 10 times, if it didn't CAS successfully, it will fall back to log. And this is like mixed implementation. Because you don't want to have wasted work. So you have concurrent link queue, which is basically the Michael's code implementation, and link transfer queue, which are log-free in the JDK.
So when do you do it? Easy. When you really need to max out some performance out of a CPU. When you want to explore
But watch out for the contention.
Watch out for contention and watch out for who does what and benchmark because it might not be faster. When you want to explore a cool subject with a friend that you've known for years but you've never done a talk together, that's our case right now. When you want to learn cool things about the hardware and see a lot of assembly and see a lot of perf output and just explore and enjoy, if that's fun to you, then yes, let's talk more. Also, when latency numbers are important for you, I would again defer latency-specific things to LMAX people because they care about it at work a lot, and to you because you do performance at the database.
Well, sometimes. On our case, the problem is disk.
What else? Do we actually have time for questions?
Yeah.
Yes, we do. I declare we can take over a bit of the break. So I permit ourselves. This is not abuse of power, this is pursuit of knowledge. So does the CAS code size start to grow geometrically if we have 3, 4, n operations that must be done in one transaction? Excellent question, whoever asked it. Well, the trick is you don't
Fall
want
back to logs.
you don't want what you want to do is publish the new state in a single or as little steps as possible. If you have to publish everything as an atomic, and there is a lot of them, the complexity of this overlapping with that becomes unmanageable, and then synchronized even would be simpler.
Yeah.
And as he said, use traditional approach. If you can model your changes as an update to an object graph and publish that new graph in a single flip,
It's
it's great.
But if you want to protect more than 2 resources, like you see in the example with the Michael Scott queue, we were protecting 2 resources, the end of the node, the next field on the node, and the tail. So this is still fine, but if you want to protect more than 2, then the amount of cars and while loops will be impossible, so fall back to locking.
In your while true loop, is there something missing, or am I mistaken? You're probably not mistaken. The example code is exactly that. It's example code. The production-ready implementations were listed with GitHub links. Our code was not listed with a GitHub link, therefore it's probably buggy and you should not use it. It's only to demonstrate an idea. And can't the other thread start this process just after you did the check? I don't remember what we were showing back then, but maybe those were examples to demonstrate a problem, not to be foolproof. That exhausts the questions. Thank you.
Thank you very much.